Hey guys, welcome to Brain Attic. Today we have another set of problems. Such problems are very common in competitive exams and mathematical olympiads. So if you do want to give it a try, you can pause the video here and you can give it a try. If you want to see the solution, let's begin solving the problem. So we have two questions over here. The first question says that we have two positive integers m and n, and the relation between the two are given as m plus n whole divided by m square plus mn plus n square is equal to 4 by 49. Then find m plus n. In the second question, we are again given two integers m comma n, where the relation between the two is m less than equal to n square by 4. Also, every prime divisor of m is less than or equal to n. We need to show that m divides n factorial. So we'll solve the problem one by one. Let us begin with problem number 1. Let us make an assumption. Assume m plus n is equal to 4k and m square plus mn plus n square is equal to 49k. We call it equation 1 and we call this equation 2, Roman 2. This is a bit unclear. So if we square m plus n, we get m square plus 2mn plus n square, which is equal to 16k. And if we just solve it for mn, we get 16 k square minus m square plus mn plus n square, which we know as 49k. Since m and n are positive integers, then the product of the two has to be positive as well. Therefore, we get 16k square minus 49k is greater than 0. This implies that k is greater than 3. Now we have another identity for mn, which is nothing but m plus n by 2 whole square minus m minus n by 2 whole square. Now, we know that a square can never be negative. Therefore, we may confidently say that m minus n whole square divided m minus n divided by 2 whole square is greater than equal to 0. Using the above equation, we can put in this inequality as m plus n divided by 2 whole square minus mn greater than equal to 0. Now we know m plus n as 4k and m minus mn we have found out to be 16k square minus 49k. Now if we solve this, we end up with 49, oh I missed a k here, 49k minus 12k square is greater than equal to 0. This gives us that k is less than equal to 4. Now, k must be an integer. Therefore, k is equal to 4. Now we already know that m plus n is equal to 4k. Therefore, m plus n is equal to 16. This is our answer. Just to validate, we were given m plus n, m square plus mn plus n square, which is 4k by 49k. Instead, if I write 16 divided by 196, which is nothing but 4 by 49. Now going to the next problem, problem number 2. So here we have to prove that pk divides n factorial, where p is all the prime divisors of m and k is an integer which is greater than equal to 1. So if we say for k is equal to 1, let's start with k is equal to 1. It will be a very simple proof because we already know that p is less than equal to n and the divisor P will definitely be there in n factorial. If you want to dig deep, suppose n is equal to 4. So n factorial is equal to 4 into 3 into 2 into 1. So all the prime which is less than n will exist in the power 1. So for k is equal to 1, we are able to show this. Now suppose k is n is greater than equal to kp, then at least k of the numbers 1 to n are multiples of p. If you didn't understand the statement, we'll see it. Then it is sufficient that pk divides n factorial. So if you didn't understand the statement, we'll make it clear with taking up some examples. Suppose k is equal to 4 and p, which is 2, a prime number. Now the product of the two, n is greater than equal to 8, using this equation. Let us say this is capital A, equation capital A. Now n factorial will have 8, 7, 6, 5, 4, 3, 2 and 1. Now if you see, 2 is my prime number and it appears, the multiples of which appears at least 4 times. Let us take another example. Suppose k is again equal to 4 and p is equal to 3, and we take n is equal to 13 this time, which is satisfying n greater than equal to 12. So n factorial will have 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2 and 1. Now if you see, 3 appears how many times? Once. Multiples of 3 appears how many times? You'll see 2, 3 and 4 times. So this assumption is correct and it is sufficient enough to prove that pk divides n factorial. Using this, we have an relation between m and n, which is m is less than equal to n squared by 4. This directly implies that pk is less than equal to n squared by 4, because p to the power k divides m. Now by rearranging, we can get n is greater than equal to 2 under root p to the power k. So we already made an assumption that n is greater than equal to kp. We got another one, equation p, from equation A. Now we can very well say that 2 under root pk is greater than equal to kp. This directly implies that p k minus 2 by 2 is greater than equal to k by 2. So if we are able to prove this condition, then we can very well say that pk divides n factorial, if we are able to prove this inequality. Now we'll take case on a case-to-case basis. Suppose k is equal to 2, then we end up with a relation like 1 greater than equal to 1, which satisfies. Now let us take a condition that k is greater than equal to 4. For all conditions k is greater than equal to 4, we'll apply Bernoulli's inequality here. So for p k minus 2 by 2 to the power k minus 2 by 2, we can write this as 1 plus p minus 1 whole bracket k minus 2 divided by 2, which is definitely greater than 1 plus k minus 2 whole divided by 2 into p minus 1. This is definitely greater than k by 2. So we have proved for k equal to 1, we have proved for k is equal to 2, we have proved for all the cases for k greater than equal to 4. Finally, for k is equal to 3, we may see that if k is equal to 3 and p is equal to 2, then we have m greater than equal to 8 and n greater than equal to 6. And n factorial is certainly divisible by 8. Hence, we have shown that pk divides n factorial. Thank you.